All right. 3-7. Simple stuff. You'll like this one. Well, you will enjoy it more than the rest of this chapter. Let's put it that way. What do they call it? Modeling using variation. There are 3 types of modeling using variation, or variation type problems. And they generally come up in like chemistry class. It's a big variation topic. Also physics. So there's direct variation. Do they call it inverse or indirect? Be careful with my phrasing. Do they call it inverse? Inverse variation. Inverse and jointly. Or joint variation. So basically there's really only 3 things to remember. The basic setup of a direct variation is y equals kx. K is constant of variation. In other words, it's a fixed number. Once you have your formula, K becomes a fixed value and never changes ever again. That's what it means to be a constant. So if I say 2 things very directly, the first thing you write down is somewhat of the form where y and x are your variables and k is your variation. You would set it up something like y equals kx. Now y and x can change. Like if you're saying weight varies with height, then I would say w equals kh. So w would represent weight and h would represent height. You know, the taller you are, the heavier you are, I think, basically, generally. Inverse variation, well, another relationship with the direct. As x gets bigger, what happens to y? If x is 1, then 2, then 3, whatever k is, it doesn't matter. As x gets bigger, what happens to y? It gets bigger. So as x gets bigger, y gets bigger. As y gets smaller, so does x. So they either both go up or both go down at the same time. Inverse, on the other hand, most books write it this way. Y equals k over x. Another way of writing it is xy is equal to k. Some formats come in that way, where you multiply the 2 variables and it equals a constant. It's better writing it the first way because here, if x gets bigger, it's in the bottom of a fraction. If you make the bottom of a fraction bigger, what happens to its value? It gets smaller. So as x gets bigger, y gets smaller. As x gets smaller, y gets bigger. So that's why it's called inversely related. Joint variation is usually a relationship between 3 things. And the last one we're going to call z. So you get y equals kxz. Now this one's a little more confusing. If x gets bigger, y doesn't necessarily have to get bigger because z could have got smaller. So it's a combination of xz getting bigger that makes y bigger, or xz getting smaller making y smaller. But it's a little bit more complex than direct and inverse. A direct relationship. The more hours you work, the more money you make. If you earned $30 an hour, would that be nice? $30 an hour? I used to charge $20 an hour for tutoring. I think. Maybe it was 25. I could make some good money. So if you are charging $25 an hour, call it T for total. No matter, depending on how many hours you work, that would tell you how much total money you made. So when you make an hourly wage, that's a direct relationship. And your constant would be $25 an hour. So if you work 2 hours, you would make $50. If you work 3 hours, you would make $75, and so forth and so on. What would be an inverse relationship that you're used to, that you don't even think about? Is it worth it to speed to Tarboro to Rocky Mountain? How many of you drive way over the speed limit? Come on, raise your hand. I know you do. You're smiling. That's why I know you do. Jenna? Yeah, you're a race car driver. I know you do too. I bet you sped to the beach. This relationship says if x is how fast you're going, then y is how much time you're spending on the road. So in other words, the faster you go, the less time on the highway, right? And a lot of people think, well, if I go 5 or 10 miles per hour over the speed limit, I'm going to get there quicker. And technically you're right, but it might only be saving you like 5 minutes. From Tarboro to Rocky Mount, the maximum time you can save, give or take a little speed, is about 2 to 3 minutes, which is sitting at a stoplight, if you think about it. So there's no point in actually speeding from Tarboro to Rocky Mount. Now, maybe from here to the beach, that's like, what, 2.5 hours? You might save 10 minutes, 15 minutes, maybe, tops, if you, how fast did you drive? Huh? You didn't drive? You didn't pay attention?
Oh, she was speeding, but it won't.
Oh, she was speeding. But technically, speeding gets you absolutely nowhere faster than, you would think it would get you there faster. It kind of does, but not as fast as you really. I love driving to work at 8 o'clock in the morning because people are flying by me on Sunset thinking they're going to get to work on time. Impossible. So an inverse relationship would be distance equals rate times time. And then you solve for time and you get y equals k over x. Jointly, I don't have a really good example of that one. Not off the top of my head, at least. All right. So let's do a couple examples of how these set up. And you have to be a little cautious how they set up. Do you remember the constraint objective problems? There would be 2 parts to it, and you'd solve one of them and plug it into the other one. This is somewhat similar to it. So these all have 2 parts. But it's not as clear as the constraint objective setup. The constraint was always a physical number that you started with, and you designed a constraint around it, and the objective was what you were trying to maximize or minimize. So it made it kind of simple in the word that you read. These things are a little bit more confusing because it has a lot of numbers, and you have to separate it into 2 parts automatically. The part that, part 1, find the constant of variation. Once you find that constant of variation, kind of like that $25 an hour over here, it never ever changes for the rest of that problem. So k is going to be a fixed value. You cannot change it after you find it. It is not a variable. It is a constant, which is totally different. And I think a lot of people get confused with that because it's still represented by a letter. But we treat x's and y's as variables. We're going to treat k totally different. Part 2, you generally find one of the variables when given the other or others, depending if we're talking about inverse, direct, or jointly. Oh, and you can do a mixture of these things too. You can have one variable doing a direct variation along with another variable that's inversely related to it. We'll get to those eventually. But they all break down into 2 parts. Find that k value, then find one of the variables given the second one. Okay, so for example, given y varies directly as the square root of x, and y equals 8 when x equals 4. Find y when x equals 16. Pretty much how these problems can be written out. Now, x and y can become words like width, height, weight, anything like that, gravity. So you have to separate it into the 2 parts. part 1, finding the k value. And it usually separates literally where the period is. Finding the k value is going to come from these two. Finding the other variable is going to come from this information. And you have to keep these two pieces separate. You cannot put them together as one problem. They're two separate parts. So here's part 1. And I need to set up my direct variation formula. It's not going to look exactly like y equals kx. So when it says given y varies directly as the square root of x, it's going to look similar to y equals kx, but it's not going to be exact. So how am I going to write it? Well, it says y varies directly, so at least I get y equals k, as the square root of x. So what do I write next? Take a guess. Square root of x. So this statement here says in mathematical language that y varies directly as the square root of x. Y equals k squared of x. From the part 1, you're going to plug in what y is equal to and what x is equal to at an instance, I should say. So substitute in y, well, that's 8. K, we don't know anything about that. Substitute in x, that's 4. Solve for k. What's k equal? 4. Square root of 4 is 2, divide it across, and you get k is equal to 4. Once you get k is equal to 4, this is a fixed value. For the rest of this problem, k is always going to equal 4. All right, this is part 2. When you set up part 2, you start off the same way. Y equals k square roots of x. And you plug in what you know for part 2. Well, part 2 only tells you that x is equal to 16. So plug in what you know. Y equals but k is 4. It's guaranteed to be 4 for the rest of the problem. So k becomes 4. Square root of 16. Square root of 16 is 4. 4 times 4 is? So y is going to equal 16 when x is equal to 16. They become the same value. And that's how they all work out. What confuses people? They see the y, they see the x, and then they see another variable with a number. And they try to use all three of them at the same time. And you can't do it. It has to be two totally separate parts. Not that bad, right? It's easier than polynomials. All right. I'm not sure if I spelled that right. I think there's a key there. Oh, time varies inversely as rate, and t equals 0.25 when r equals 14. Find t at 14. Why would I pick 14? No, I don't want 14. 60. Yeah. In other words, 60 miles per hour. 60 miles per hour. And then 0.25 is hours. Find t when r is equal to 70 miles per hour. This is the problem. I'm going to show you that it's worthless to actually, speed. So when I say time varies inversely, or invert, that's the best way to say it. When time varies inversely is the rate, you're going to say t, I wrote little t and big T. Which one looks better to you, little t or big T? Big T I like little t, but change that to big T. Big T varies inversely. Now when you vary inversely, what's the other side have to look like? Look back in your notes. K over X. In this case, it would be K over R. Nothing fancy happening to the R. Plug in what you know. Well, what do I know? Do I know T? 0.25. Don't be using anything on the second part of the problem. 0.25. Do I know K? No, that's what I'm looking for. Do I know R? 60. How do I solve for K? Multiply both sides by 60. 1/4 of 60 is 15. So K is equal to 15. Does anybody know what that 15 really represents? So sad. Seconds. Nope. Okay, think about this for a second. Some number divided by 60 miles per hour is equal to 0.25 hours. Miles. This is actually 15 miles. So basically this problem is saying, if I change my speed, how long is it going to take me to travel 15 miles, which is technically the distance between Tarboro and Rocky Mount, maybe off by a mile. All right, so K is equal to 15. Then I start all over again. I say, well, T is equal to K over R. The second part of the problem is, what if I increase my speed to 70 miles per hour? Find T. So that becomes T equals, what is K in this case? 15. It stays that way for the rest of this problem. R in this case, 70. So what's 15 divided by 70? 0.214. 0.214? All right, that's hours, by the way. How do I convert that to minutes? Because I have no idea what the heck 0.214 hours is. How would you convert it to minutes? Let's do something easy. 0.25 of an hour is how much of an hour? Quarter. So how do I change it to 15 minutes? Well, you take a quarter and you multiply it by 60, and a quarter times 60 is 15. It's 15. That's why you get 15 minutes out of it. A quarter of an hour is 15 minutes because 1/4 of 60 is 15. So you take 0.214 and you multiply it by 60. So it's 0.214 multiplied by 60. Basically 13 minutes, right? So increasing your speed by 10 miles per hour over a 15-mile period saves you exactly 2 minutes. That's 10 miles per hour faster than originally. What's cool is, watch this, ready? Do T equals 15 divided by 80. Oh, a lot of people are like, oh, the speed limit's 70, I can do 80. Well, some people do it, that's scary. So what's 15 divided by 80? 0.188. Multiply that by 60. How much? 11.25 minutes. All right. So if you went from 60 to 7, you save yourself exactly 2 minutes. Well, close enough to 2 minutes. When you go from 70 to 80, you're saving yourself less than 2 minutes. 1 minute, 0.75. So 1 minute and 45 seconds. So the faster you go, the less time you actually save. Your time savings goes down as you speed up. It's a weird, it does make sense. The graph of this thing looks like this. So if you go really, really slow, it takes you a really, really long time. As you get faster and faster, from this point to this point, there's not much difference in height. So you save less time for the same interval as you go to the right. So if you pick between this point and this point, they're even closer. So as you go faster and faster, you're making up less time. Kind of weird. People don't get that relationship. They think, oh, if I go faster, I'll get there faster. And technically, not really true. Well, I mean, it is kind of true, but not over short distances for sure. Remember, 2 minutes is sitting at a stoplight. And therefore, once you hit a stoplight, you lost all that time you just saved. The other relationship is this. The faster you go, the more gas you waste. And it doesn't go linearly. It goes, I think it's quadratically. You think? Because air resistance is a square relationship. So if you think about the cost of speeding, it's kind of like this. It's really close to that. The faster you go, the more it's going to cost you in gas. Because your car is pushing. Have you ever run into the wind? I had a track coach. It would be a windy day, and he would make us run into it. And that is the hardest thing in the world because the wind's trying to push you back. Same thing with your car. The faster you drive with it, the increases on your wind pressure on your car goes up. Therefore, your engine has to work harder, and therefore you use more gas. I remember one time I drove my friend. He drove up from New York City to Syracuse, and he did it in 3 hours. He went 80 miles per hour the whole way. He went through 3 tanks of gas. I went back at 60 miles per hour, 1 tank. He's like, how'd you do that? I went the speed limit. People don't understand wind resistance. It's very dangerous. Well, for a car. So when the gas prices get up to $4, I'm going to go 5 miles per hour below the speed limit. And I will still get to Tarboro 2 minutes after you and save twice as much money. I'm the smart one. And I don't mind people blowing by me. Yeah, good luck. And I usually catch up to them, which is even funnier. All right, so that would be varies inversely. So let's do one out of the book.
Yeah, light.
What's that?
Usually catch up with them at the light.
Yeah, that's where I usually go. Yeah, we saw. Do one out of the book. Oh, darn it. What looks good? No, that was boring. 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 Ooh, that's good. Number 30. The illumination provided by a car's headlights varies inversely. Since I have the word here, I might as well spell it right. Inversely. As the square of the distance from the headlight. Okay. It produces that's a different way of writing it. 3.75 foot candles. Personally, I think there should be a dash in there, but they wrote it as foot candles. I've never heard of a foot candle. At 40 feet. What is the illumination? At 50 feet. Candles. Now I've heard of candles before. The brightness of a light is measured by the brightness of a candle. So one of these lights probably produce about 50 candles. If you had 50 candles stacked up together, it would be about as bright as those lights. Now a foot candle, I'm not quite sure about that. It's probably the candles times how far away you are from it, so they call it a foot candle for illumination. I don't know. It's not the best terminology. Generally, they change things into metric system, and it usually becomes something like newtons or joules or something like that. Okay. So we start off at the beginning. Headlights varies inversely as the square of the distance. What do you want to represent headlights illumination? You have 2 choices. H or I. Which one would you choose? H for headlights, I for illumination. Which one? The headlights illumination varies inversely. So what variable do you want to represent headlights illumination? H for headlights or I for illumination? H, all right. So H varies inversely, so that equals The square of the distance from the light. Well, d I'm going to use as distance. So how do I write varies inversely with d as distance? What's inversely look like? Not square root of.
What is a square of?
Square of, not square root of. So this would be k over d squared. So as you get further away, the illumination on the bulb goes down by a square factor rather than a single factor. Okay. Plug in what you know. That would be part one. So what do I use for part one?
The head.
The 375 for the headlights, the illumination of the headlights, is equal to k, I don't know what that is, d, 40. So I write 40 squared. Don't forget the square. Now 40 squared is 1600. 1600 times 3.75. I don't have a calculator in my hand.
What'd you say?
What did you say?
40 squared is
1600.
times.
And 1600 times, because you have to multiply both sides by the denominator, cross multiply, whatever. Should come out nice.
6,000.
What is it?
6,000.
6,000? So K, the constant of illumination, I guess you could call it, is 6,000. Okay. Set up the second part of the problem. You write your formula down again. H is equal to K over D squared. And you plug in what you know for the second part of the problem. What do I know? Do I know H? No, I don't, because that's what I'm looking for. Don't be going back here. Once you use the 375 and the 40, gone. They are gone. They're done with. What you have left is finding illumination when you're 50 feet away. So, do I know H? No. Copy it down. H equals. Do I know K? That doesn't change. That's going to be 6,000. Do I know D? Yeah, 50. So I'm going to write it as 50 squared. So what's 6,000 divided by 2,500? 2.4. So H is going to equal 2.4. What? Miles? But it wasn't called illuminations in the problem. What is it? Foot candles. This is foot candles. Whatever the heck that is. Foot candles. Well, it has something to do with illumination at a certain amount of feet. But it's less luminous. This one is a little bit brighter because it's a bigger number. This one's smaller, so therefore it's not as bright. And if you've ever driven on a highway and someone has their high beams at a far distance, it doesn't bother, at least my eyes. But once they get close, they you start like turning
Yeah.
off. And then it's just a car that kind of has bad shocks in the back, and they're like, no. And then they turn on their brights, and they're like, oh my god, it's horrible. I can't see now. Oh well. So all these problems work out basically the same. They only get tricky when they start dealing with multiple variations. Let me find one with multiple variations. And then we'll take our quiz. Yay! Alright, multiple variations. I think it's used to count. How many tell that you? Ooh, 32 is a multiple one. This one's interesting. One's intelligence quotient varies directly as a person's mental age and inversely as a person's chronological age. A person with mental age 25 years old and a chron age of 20 has an IQ of 125. What is the chronological age of a person with a mental age of 40 and an IQ of 80? That would be the question. Now notice this problem has 3 variables in it, not just the 2 that we're used to. What's going on here is we have a direct variation and an inverse variation in the same problem. And basically all you have to remember is direct variations go in the top of the fraction, inverse relations go in the bottom of the fraction. Okay, so what do I want to use as mental age? What letter? M sounds good. What letter do I want to use for chronological age? C. And then of course IQ, I guess we could just represent with IQ. I mean, just realize it's one thing, IQ. All right, so IQ as a single variable, even though it's 2 letters, it represents your IQ, is equal to, get that K in there, that's guaranteed one way or the other. Now, what's cool about K is it doesn't matter if you put it in the top or the bottom. It'll just change value, but it'll balance the equation correctly. Put it in the top though for safekeeping. All right, IQ varies directly as the mental age, so where does M go? Top or bottom? Top. And inversely as chronological age, so that goes in the bottom, C. So that's my formula set up for IQ. I think this is an actual formula in psychology. Seems familiar. I only took Psych 1 though. Oh no, I took Abnormal Psych and I think one after that. Abnormal Psych was kind of cool. I'm one of them. Abnormal. You be quiet back there. Look at your hair. You look like you put your fingers in a socket. See, if I put my fingers in a socket, exactly the same. Exactly the same. Now, for the first part of the problem, do I know the IQ? What is it? 125. Oops, it's not working. Other marker. 125. Do I know K? No. Do I know the mental age? 25. Do I know the chronological age? Chronological. 20. Solve for K. What would you do first? You could do that. Or reduce 25 over 20. There's lots of different ways. But if you multiply by 20, that'll work too. This side becomes multiply by 20. 2,500 is equal to 25K. And then divide both sides by 25. And you get K is equal to 100. Okay. Remember, IQs are meaned or centered at 100. If you're above 100, you're above average intelligence. If you're below 100, you're below average intelligence. Does that mean people at 100 are stupid? No. They're average. Average human beings on the planet Earth. Nothing wrong with being average, by the way. Getting a C in a class is not a bad thing. People don't understand. C's are the average grade, so most students are going to get a C. Everybody's like, I want an A. I want an A. Not everybody gets A's. All right, start all over again. IQ is equal to KM over C. Plug in what you know. Do I know the IQ? And please say no. Oh, no, please say yes. This one we actually do know. Which one's the IQ for this one now? 80. Do I know K? Yes. Is that 100? That doesn't change. Do I know M? The mental age for the second part is 40. And we're looking for chronological age. So, how do you solve for C? Multiply both sides by C. That's 4,000. And C would then equal 50? Right. Is it 50?
Yeah.
Is it like the housing?
Yes.
Be quiet. So what's 50 represent? So 50 years old. And this is how old he really is.